Streaming test. Please ignore streaming test. minutes until dawn. That clock's wrong, that clock's right.
I can't speak anymore now? It's on already?
It's live now.
Because I don't hear anything. I don't hear anything if I'm whispering.
Ja, ich habe es sehr leise aufgedreht.
Ah, okay. Das heißt, ich kann jetzt noch sprechen. Hm? You just...
Hello everybody, and welcome to our session on emotion and computing. My name is Jochen Steffens. I'm a postdoc at the Technical University of Berlin in Germany, and I'm happy to welcome our first speaker, Elke Lange from the Max Planck Institute for Periodic Aesthetics. And Elke, the floor is yours.
Thank you. So, hello everybody. Thanks for coming. Some time ago, Klaus Wheeler and I, we came across the question, can the perception of emotional expression in music be modeled using automatically extracted features, for example, from music information retrieval tools? There's, of course, a huge possibility of applications, for example, causal explanations for music emotion expressions, consumer applications, and what I was particularly interested in is stimulus selection for experimental research. So Klaus and I, we decided to have a closer look onto the question, how reliable and precise is the modeling of emotional expression in music? This talk will highlight some key issues, but only few, and all details you can find in our forthcoming paper in music perception. And please also check out our interactive visualization, and you will find the link in Moodle. In our approach, we decided to gather expert ratings for a wide range of ecological valid music stimuli, and to take upon the role of a mere naive researcher, use out-of-the-box audio feature extraction, and compare and model emotional expression ratings with extracted audio features and ratings of perceived musical features. Of course, this question is not new at all. So predicting perceived emotional expression, there's really a huge body of literature on that, and I just started to write some on the bottom of the slide, but there is much, much more. Generally, there is good accuracy reported in these kind of predictive modeling. There are better predictions for arousal than valence, and there's a large array of relevant features in the MIR community, for example, note density, peak sound level, attack time, etc. And from more a perceptual side, something like tempo, tonality, and pitch are good predictors. But there is no standardized methodology. So we decided to look into a couple of key issues of a more general method. First of all, we wanted to take a closer look onto the quality of subjective ratings, then on automatized feature extraction, the selection and reduction of feature sets, the relation between the perceived and the extracted features, and modeling accounts using aggregated versus individual data. And the results section will then also follow these 4 subsections. In our study, we presented 60 musical excerpts with a duration between 43 and 61 seconds from a very broad range of styles. and they were roughly spanning the valence arousal spectrum. It was very important to us to use expert ratings, so we asked 20 professional sound engineers with a mean age of expertise of 15 years. And those sound engineers, they rated our 60 musical excerpts on 22 items from different levels. For example, a low, mid-level acoustic features like pitch, loudness, tempo, complexity of temporal progression, for example, harmonic variability, then some modal features like brightness, temperature, and tactile information, and emotional expressions, for example, angry, happy, peaceful. And they rated our items on a 7-point rating scale, which were unipolar for emotional items, spanning from 1 to 7 then, and bipolar for all others. And as already said, we used some feature extraction and we used the Mir toolbox. Coming to the results. Here you see some histograms of the ratings for Albatross from Fleetwood Mac. So on the x-axis are the 1 to 7 ratings. And for example, you can see here the angry rating for this piece of music is pretty much right skewed. This we found very often for emotion items which are not fitting very well for a specific excerpt. Interesting for us was particularly that, for example, take a look at this dark-bright figure. You see that most of the sound engineers regarded this piece of music as dark, but there were also some regarding this as bright. So 4 would be the middle in these bipolar kind of items. And there are, if you take a look at the other items, you see this kind of bimodal distribution quite often, and I just point out a few of them. If you want to do some statistic tests on this, you use, for example, the Hardigan-Stipp test for multimodality, and usually you would like to have them not to be significant. You want to have a uniform distribution with a clear mean, etc. But what you see here is that there is a really high percentage of significant Hardigan-Stipp tests for multimodality, and on the x-axis are now all 22 items. Additionally, we didn't find agreement between observers, and keep in mind these were professional sound engineers whose job it is all day long to really extract musical features. So agreement was pretty low. Altogether, you can say that we found frequent multimodal non-normal distributions. This basically means that the mean is only a crude approximation for further statistics. We found quite often right skewed distributions of emotion variables with low mean values and low agreement between raters, even for experts. Second, feature extraction. So we extracted 86 features commonly used in music research, neuroscience, and the Mir community. And our measures were the mean and the standard deviation across stimulus duration. I show you now a plot on the correlation between features. You see basically 86 by 86 correlation matrix. And so from the upper left to the lower right corner, you see this black line. This is the correlation by itself. And what is clear is that the correlation by itself is pretty high as 1. So it's dark, it's black. But there are many other fields which are black. So huge number of features are correlated. For example, with brightness, highly correlated is spectral entropy, flatness, roll-off, spread, skewness, kurtosis, centroid, etc. This is really problematic. First of all, for interpretability, 50 shades to measure brightness, and it's also problematic for statistical models. And it calls then for a feature selection or feature reduction, for example, a principal component analysis. In a third step, we compared our extracted and perceived features, and some comparison resulted in correlations of 0.45 and higher in the mean ratings, for example, loudness, tonality, roughness, and the fullness of spectrum. And at least loudness and tonality are established key features for predicting emotional expression of music. That means that the results are kind of satisfactory for mean ratings, and automatized feature extraction is related to perceived stimulus attributes. We want to point out that there was one feature which was insufficient. This is mere tempo. which is based on a not so little old algorithm maybe, but experimenter annotated tempo then correlated highly with the perceived tempo estimates of the sound engineers. So it made sense to do the modeling approach. We used regression models. So for example, we predicted mean ratings by acoustic features or individual ratings by acoustic or perceptual features. In the second case, we used linear mixed effect models to do that. And this part of the results section will be really short. So I want to point out another thing here, which is our feature selection. We had the problem that the PCA didn't result in any factor solution because of this really highly correlated structure. So we employed 4 different feature selection strategies, feature clustering. Then the second one is that we always kicked out the highest correlation. Then we just choose some features for their good interpretation, and we compare these 3 kind of logical selections with just a random selection. And this is what I'm showing you in the next figure. On the x-axis, you see the emotion ratings, like angry, sad, happy, peaceful, tender, and fearful. The lines are the 4 feature selections, so 3 which kind of made sense, 1 very random, and you see so that these goodness of fits really overlap highly. So there was no huge difference whether to select the features on a logical base or randomly. Importantly also, the root mean square prediction error is rather low. So it was 1.2 for happy, but even below 1 for all the other rated emotions. And 1 root mean square prediction error means that the predicted value would be 1 or 1 on a 7-point scale from 1 to 7, 1 to the left or to the right of the scale. So it's pretty good. And if you compare this with individual level models, so with ELMA models, where you can take individual variants into account, the root mean square prediction error increased, so it was larger. So this was something we were quite puzzled, and I show you now why this is the case. So you see here now the data points, so the means across the subjects for each song, and you see the measured means on the right side and the predicted means on the left side, and this kind of bell shape shows you the distribution, so how many data points were there. And you see that they fit pretty nicely. So they are all ranging between 1 and 4, and so there is a rather low root mean square prediction error and a high explained variance. But if you now go into the individual level, the ELMA models, you take the individual ratings, so each rating from 1 to 7 into account, and try to predict something which is based on the mean and some deviation on the mean. So how to predict something which is spanning 1 to 7, and to predict then something which is spanning 1 to 4, this naturally increases the root mean square prediction error and decreases the variance. Okay, so summary. Subjective ratings of music are often inconsistent. Acoustic features are highly correlated, and that means that the interpretation is also often unclear. Loudness, tonality, and roughness correlated highly with analog extracted features. And basic emotion perception can be predicted on the group level using, for example, tempo, mode, loudness, and brightness, which are key features in music psychology. The take-home message is then, acoustic features are useful, and I also want to point out that the MIR toolbox is really very helpful. It's a helpful tool in music psychological applications, but it should be applied with care and some understanding of the underlying algorithms. So for example, beware of suggestive naming and cross-check higher level features, particularly tempo and pulse clarity, something like that. And individual differences can be large, so modeling is then rather sensible on the group and not on the individual level. Thank you for your attention.
Thank you very much, Elke. We have questions. Maybe just I bring you the microphone. Just wait a second, please.
You used the experts
Yes.
sound engineers, and you thought that they would agree, but probably laymen would agree more because they are more schematic thinking or hearing, and experts are more, because they're expert, they're more special or something.
Yeah, I want to go back to one of those slides so to show you more. I'm not good in this mouse. What are you doing?
Sharing your screen. Because we want to share.
Okay. And can you go here to the screenish, which is more up, and this one. So yeah, so the argument was that we thought that experts would agree, but the layman might agree more. So we were pretty astonished because items which we asked were, for example, loud, soft, pitch, high versus low, the spectrum rather wide or sparse, rather wide or small and sparse or not so sparse, stuff like that. And I think these are key features which sound engineers really have to know to do their job properly. Also, like if they're in a live context environment and need to figure out where to, how to use their tools. So I think yes, we could do it with laymen, but I would expect them, to even be more heterogeneous. But that is a matter of experimental, or empirical research then.
Okay, thank you. Further questions?
I think the girl with the white shirt.
1 second.
is next.
Thank you for a really interesting talk. I was wondering what music you use and what different genres perhaps, because one reason which could also be the differences between the experts, maybe because they themselves have an opinion on what's appropriate for a certain genre or a certain band even, or...
So we wait a second so we see the screen again. Okay, and then, okay, I'm getting better at that. So, can you see the screen again? Yeah, you can. Gone. Here. So I listed a few genres here. So it was blues, country, electronica, metal, rock, pop, classical music. We had from the classical music, we had some more romantic music. We also had 4 items more from the contemporary music. So we really tried to span a really huge range of different styles.
So do you think perhaps the expertise in these different styles may have also influenced their different...
We asked about their, for example, for their liking, preferences, and they showed a very broad preference as well. So I think, I'm not sure about that, but of course there are different styles, for example, film music, which are composed to specifically carry emotions, and then maybe the judgments will be much easier for them.
Okay, thank you. Unfortunately, discussion time is over. Thank you again. Further questions can be asked in Moodle. So thank you again, Elke.
Yeah, you're welcome.
Do I have to put this on myself?
And you can put it in a pocket or...
Okay, cool. Is that fine
Is that
how
okay
it
for
is?
you?
Yeah.
Ja, ich dachte, das nur, weil du jetzt hier das sagst.
Alright.
Dann lass uns doch einfach
Is that okay for you?
Yep.
So, presentation.
Okay, then we come to the second talk of the session. Just welcome Will Randall from the University of Jyväskylä. He's going to present his great app, MuPsych app, so I'm very excited about this talk. Will, please.
Okay, thanks. So yeah, today I'll be talking about experience sampling with the MuPsych app, which I always do, but specifically we'll be looking at the new model that we're building of emotional outcomes of personal music listening. So a very quick rationale. This comes from the Music Consumer Insight report of last September, and it was just how many people have used a smartphone to listen to music in the last couple of months, I think it was. And as you can see, those percentages are really quite high. And then when we break it down by age group, as you might expect, all the kids these days are listening to music on smartphones. But even as you get older, even up to 50, the majority of people have listened to music on a smartphone, which is quite shocking. And given that we know that music has a powerful influence on our emotional states, I think it's really important that we understand like how this style of listening, which a lot of people are doing, influences our moods. So to do exactly that, I've been using the mobile phone app MuPsych. This is an event-based sampling of music listening. So when a participant listens to music on their phone, at that exact moment, we present them with questions about their mood and context and so forth. So this is real-time and ecologically valid data because these people are out there in the real world listening to their own music on their own phone. It has minimal retrospective recall bias, which is a really big problem with all the online surveys that all of us use. And the good thing about the new platform is that it's integrated with streaming services, so people can use any music player on their phone and we will sample their experience. So we'll quickly go through all the screens in the app just to give you an idea of the data that we're collecting. So first of all, at that exact moment they start listening to music, we ask them about their emotional state. So they rate their valence and arousal, and then based on that we present them with a list of categorical mood states from which they present a single most appropriate one. So this means that at 0 and 5 minutes we measure valence, arousal of mood, and also the intensity of this selected mood state. So the change in those three things over 5 minutes is our main outcome measure. Also, of course, if they're listening after the 5 minutes, we ask them about their context. So who is listening, where they are, and what they are doing at the time. We, of course, asked about the music. We actually collect the music data itself objectively, but we ask them, for example, the subjectively perceived valence and arousal of the music, how much attention they're paying, how familiar they are, and how much they're enjoying it. Also more complex things such as what kind of memory they associate with the music and how much choice or control did they have in hearing it, which if you ask Amanda Krauss, she'll tell you is very important. And a couple of screens straight from the MuPsych literature. So on the left we have the underlying mechanisms, which is the work of Patrick Uslin. And Patrick and I worked on making this an intuitive and very easy to respond to self-report list, because you can't really ask someone if they've just had a brainstem reflex, has to be in slightly better words. And on the right we've got emotion regulation strategies, which was put together by Suvi Saracalio and Margarita Baltazar. And we also created a specific interface for MuPsych to assess reasons for listening very quickly. So across 3 screens, we've got a main reason category, a specific reason, and any other additional reasons. Okay, so that's all collected when they're listening to music. We also have non-music, randomly timed samples for a control. And we also have a battery of surveys, so all the psychometric tests and questionnaires, all the classics, so personality, demographics, musical experience, quality of life, mental health indicators, and so on. So we collect loads of data through the app. So this is just one study. I'll show later there are multiple studies on the app, but this is just one that we've started to build this new version of the model. So participants installed the app on their phone, and they received these experience sampling reports and surveys over a 2-week collection period, and we analysed it with multi-level modelling. So the next few slides are just to give you an idea of some of the data we can explore using this app. This is similar to some of the graphs in the excellent ESM study of 2008 by Uslin. comparing music in blue and non-music episodes in red, and the frequency of activities that they're doing when they're listening to music or not. So I'll just quickly go through these. This is the same again, but for initial mood. So there's certain moods that people are in when they listen to music as compared to non-music. This is the change in mood for the most frequent mood states over the 5 minutes of listening. Again, I'm just going to quickly get through. And the most frequently listened to reasons. But what we're really interested in is not just these single variables, but how they all work together in this multi-level model. This was published by Nikki Ricard and myself last year, and it actually looks at the emotional outcomes of music listening on 2 levels. So you've got the experience level that takes into account the context and the initial mood and their reasons and so forth. And then combined with that, you've got the listener level where all the demographics and personality go in. So a major finding from that study was actually 95% of the variance in emotional outcome is explained on the experience level, which for us really suggests that anyone studying music and emotion should really consider these context variables. So basically, we've just started to rebuild this model, but much better, hopefully. And here are the early results. So valence change and arousal change are predicted by their respective initial mood state. So the overall general influence of listening to music seems to be bringing it back to a neutral level. But of course, this is taking everything into account. So to get a real idea, we need to break it down by initial mood state or reason for listening, which I won't get into today, but that's what you really need to get the actual picture of how people are listening. Okay, enjoyment obviously went into predicting valence and arousal change. So these are the music variables and their predictors. So interestingly, music valence was predicted by initial valence and music arousal by initial arousal, which kind of supports the idea that people select music that's congruent to their current mood. Another interesting finding is that enjoyment of music was strongly predicted by listening to music at work, and that might be partially explained by the fact that listening at work also was associated with very familiar music. And also there's some findings related to attention and traveling or driving. So I'll go on to the predictors for reasons for listening. So again, there's a lot of activity-related findings here. So when people were traveling or exercising, their reason was not for enjoyment, but it was actually specifically for music for that activity. And it wasn't to raise energy either when they were traveling. And similarly, when people were listening at home, they more likely to use it to relax. There's a strong association with listening to relax and not to raise energy. And these are the regulation strategies and their predictors. And the interesting findings here all relate to a lot of the transport. So entertainment and driving is related to transport and driving is related to the entertainment strategy, and transport, walking and driving are not related to the, or negatively associated with the revival strategy. Okay, so that is a very quick overview of what we're doing, building this model, remaking the new model with a better app and a lot more variables. So that's just one study, but the app is now available for any music researchers, so you can create your own custom study through the app. So you make your own ESR screens or surveys and put them in. We've had some really interesting apps, studies running it through so far, looking at all sorts of different things. Anyway, if you're interested in that at all, check out the MuPsych website. And just a minute or so on what we're doing with this data. So we're building this model from all this subjectively reported data from the app. But there's really no objective data at all except for the song details that we collect. So we're going to take those and combine it with a set of objective data through music information retrieval. So we're looking at the music features and also the bigger data sets like semantic tagging. Yeah, we're going to combine basically all of my subjective data with objective musical data. And then we're going to build this into a machine learning model that is going to be used to curate playlists that will assist adolescents in regulating their emotions with music. And this model is going to be guided from directives that we draw from the music and health and music therapy literature. So yes, we've just been funded to do that, so we'll be doing that for the next couple of years. That's about it. Thank you.
Thank you very much, Will. There is enough time for questions. Yes, just come up.
Hi, William. Thanks for your talk. I was wondering something about the perennial ecological validity problem. Don't you think that maybe by inviting the subjects to self-reflecting on their mood, that this might affect the music experience? What I mean is that, putting another way, you are changing the context by asking about the initial mood, and the music experience might be affected by that somehow in uncontrollable ways. How do you see that?
Sure, absolutely. I think anytime you're going for ecological validity, there'll be a trade-off with intrusiveness. I think anytime you try to observe something, you've got to alter it in some way. What we're trying to do is make it as minimal as possible. So I went through all the screens, but a lot of the studies just have like the very basic, what's your mood right now? In the future, I would love for to not ask them a lot of the questions. So I guess the idea is to phase out a lot of the questions. So instead of asking them about the music, I can reduce those questions and use that data from MIR to replace what they're saying about the music. And with mood also, people with smartwatches or any, the facial recognition stuff that will be able to automatically assess mood. I think, there always is that trade-off between ecological validity and intrusiveness. And I see this as, at the moment, the best we've got is just asking people, but eventually it'll be phased out into automated mood detection and that kind of thing. So yeah, I agree that there's intrusiveness. There always has to be if you're getting people when they're actually doing the activity.
Okay, any other further questions? And just here? Okay. Then I might have a question. In your model on music listening behavior, you're also introducing some kind of mediation effects?
Yeah, so...
How are you going to test for these in your...
Yeah, it's really, like you saw, it's only 36 participants so far. It is very early. We're going to build this for a long time yet. Yeah, in the early one, in the first model, there was like an interaction of initial mood and music mood on the outcome. So yeah, we'll be keeping an eye out for things like that, but I can't really say what's there yet.
And the study, how many prompts did the participants receive over the course of the day?
With this study, it's you kind of determine the gap between when they complete a report, you block the app for a certain period of time. So for this study, it was, I think, 3 or 4 hours, but people who are setting up their own custom studies can set that for as long as they want. So you can, if they do one report, you can block it out for a day or more if you want. But yeah, I think like 3 or 4 hours means that you get most listening experiences, but if you don't want to annoy your participants so much, you can definitely spread them out a bit more.
Okay, last chance for questions. Yes, Melanie? Wait a second.
Maybe a more technical one. Last time you presented the MuPsych as Spotify plugin, right? At the DGM conference. Does it still work as a plugin for Spotify? Or
it's not. It's not so much. I mean, the last version of the app, they had to log in through Spotify. Now it just collects the song data automatically. So it works. I mean, it just looks at the system music that's playing and gets the data from that. With the last version, if they logged in, we could get more of the like the metadata stuff from Spotify, but we haven't got that in this one yet. So we just want to get the song details and then analyze that through the like semantic tagging kind of models and that kind of thing. So yeah, I mean, the point is that it works whatever music player. Like if the phone detects music on the device, it'll send these alerts, so you don't actually have to log into anything. Or
Okay.
Thanks.
Okay. Any further questions? If this is not the case, thank you again, Will.
But then we'll have to switch. Yeah. Yeah. No, but you can come here. No, because there's the just go in behind me or somewhere. I find it so rude showing these cards up. I'm just like, sorry.
So if you want to move, remember to take that with you. Okay. So we need your presentation.
Jochen Steffens, ist der Name Aljanaki jetzt richtig ausgesprochen?
Aljanaki, yes. Yeah, that's right. Okay. Can I start? No?
The music will just come in one minute, and then I will just introduce you.
Oh, okay.
And then like 10:40 or 10:39 we're going to start. Okay, we have 2 more minutes to wait. Now, in 1 minute the music will start.
Yes, okay, I see. Thank you.
Okay, now we're coming to the third and last presentation of our session. Welcome Anna Aljanaki from the Johannes Kepler University of Linz, and she's going to talk about extracting majorness as a perceptual property of music. Is Anna?
Hi, and first you're probably asking yourself what is majorness, and normally in musicology you just have this categorical modes, and you assign the music to a certain mode until it modulates or something else happens. And majorness is a term which was used before me to determine something called continuous mode, and Richard Parncut, for instance, used it to assign a property to intervals and to music pieces and to melodies, to say that they sound either minor or major, and we ignore that there are many other modes. There is no Mixolydian mode, there is no blues scales, there is nothing, there is just something that sounds more minor and more major. And one interesting part of this discussion is that normally, in order to determine what mode music is in, you need an established tonal hierarchy. But sometimes you don't. For instance, you can say that a certain chord is sounding major or minor, or a certain interval, or even a timbre of a certain sound can have sort of major and minor properties to it. So, why are we interested in this at all? Is mainly for the reasons when we want to handle large music archives. I come from music information retrieval background, where we want to get the computer to extract interesting properties from large archives, like all of the Spotify music for us, in order to do stuff with it, in order to recommend music, in order to choose a proper music for a video from a production music database. Okay, and in our terminology in music information retrieval, people often refer to every music descriptive term or feature as high, middle, or low level. This terminology is very hazy, and everyone uses it as they please. I'm going to do the same thing. So here I describe certain features or certain musical properties as being low, middle, or high level, and I'm interested in the mid-level. So whatever has very low subjectivity and can be defined by physically present musical objects is going to be low level. So it's properties of the sound, their timbre, the beats, onsets, chords. Sometimes chords are called a high-level music feature because they're difficult to extract, but in my terminology, they are low-level. Then there is a mid-level level of abstraction and mid-level feature, and everything that is defined using the low-level features is mid-level for me. So, for instance, harmony consists of chords and of melodies and a combination of all this, and it's mid-level. Rhythm consists of onsets and beats and all this stuff, and then it's mid-level. And then whatever is derived from the mid-level and can only be defined by using all the musicological factors and features and properties possible is high-level. So my point is that in order to define all the stuff on the high level, we need to be able to extract the mid-level. And whoever of you has been present on the first presentation in this session have heard about an attempt to extract or predict the mood from the features extracted by an MIR toolbox. Okay, so MIR toolbox normally tries to extract for you whatever is on the low or mid-level. But the features that are on the mid-level, such as mode, there is a feature very similar to majorness. There is a feature for dissonance and for rhythm and for other stuff. And all of them are extracted using an engineering approach where you look at a problem. For instance, we have articulation, and we want to to determine whether this note was played with a staccato or legato articulation. In order to get a computer to extract this property for us, we try to understand what is in this property and then create an algorithm that does it for us. But there is a different approach. You can do the perceptual ratings like Elke, like the first presenter did in her research. And then we know what staccato articulation sounds like for a human listener. We know what the legato articulation sounds like and what everything in between sounds like. And then we teach a computer to just recognize this property from the data without giving an explicit definition. And that's what I'm going to do for majorness. How majorness is extracted in the Major toolbox, for instance, we have this Krum-Hansel's tonal profiles. We match them to chroma feature of the music, and we try to get a best passing profile for major or for minor. Oftentimes we confuse the parallel major and minor modes, and the uncertainty of determining whether it was a major or minor mode is used to determine majorness, an engineering approach. So what I'm doing here is going to be different. I'm going to get lots and lots of musicians to tell me whether something sounds major or minor for them. And then I'm just going to get a neural network to learn whatever these people told me. You probably know some crowdsourcing platforms, maybe Amazon Mechanical Turk. This is a very similar platform, but it's based on a Russian website called Yandex, which is sort of like a Russian Google, and they have their own crowdsourcing platform. And the reason I use that is because Russian minimum wages are much smaller, so you can get much more data annotated. Also, Russia has a very good musical education system, which is free, and you don't need to hire a private teacher for a child. If a child is gifted, you can put them through music education for free for 7 years, in addition to school. So there are lots of people who know the music theory. Anyway, so then on this platform, I'm getting people to do the musical test, which lets me know their, they determine tonalities for me, and they show that they understand the terminology and things like that. And then I selected 80 people to do this experiment. And the experiment will consist of 2 parts. In the first part, we're going to give a definition of what major and minor sounds like on 100 excerpts. And then this helps me to create a scale from the most minor sounding thing to the most major sounding, and through everything in between, because everything in between is the most interesting and difficult part. And then, using the scale, we can rank lots of excerpts which can be used in order to train a neural network. And a lot are necessary. And I took 5,000. Music is coming from various genres, and it's a small excerpt, 15 seconds. For the 100 excerpts which are going to be used to create a scale, we try to get as varied music as possible. It's scattered on balance arousal plane. It's coming from all sorts of genres possible. And then what I ask people to do on Toloka, I ask them to listen to 2 excerpts, to 2 random excerpts out of the 100, and to tell me whether the one on the left or the one on the right is more minor, is sounding more minor. I give them also a definition of what is more minor by just asking them to try to imagine that they are accompanying the song, or they're writing down a lead sheet for a song, and then they want to write them in chords, and whether they will put more major or more minor chords to accompany the song. Okay, then they do that, and out of this pairwise comparisons, I can construct a ranking. Pairwise comparison is a much more reliable way of getting annotations out of people, because it's much easier to just compare two examples than to get an absolute ranking on something. To get an absolute ranking, you first need an anchor, and everyone will get their own. And then when new music comes, maybe something that you rated as 1 will turn out to be not as minor, let's say, as something that will come later. So people are afraid of using the extremes. Okay, so out of these pairwise comparisons, we get a scale. And here below, you see the scale. So it's musical examples, short examples. And then a person listens to these examples, and they try to find an example which is exactly in between. So for instance, if someone rates a song as a 2, it means that it's more major as than an example to the right, and more minor than an example to the left. Okay, and from this data, I can get my scale. And for each excerpt, I get its majorness. This is a histogram of the absolute rankings for each excerpt. The Kronbach's alpha was 0.69. The Krippendorf's alpha was like similar to the experiment in the first talk of this session. It was a low Krippendorf's alpha, which is what happens with such subjective things. Okay, then what did people hear in this music, and what they considered as majorness? Well, basically, they introduced a lot of their beliefs of what major music should sound like. So it should sound happy. And here is a correlation with the songs from Soundtracks dataset. Soundtracks dataset has soundtracks music annotated with valence, arousal, fear, sadness, and other emotions. And I had this music inside the set of the 5,000 songs in order to do this. So we have a really high correlation of majorness with happiness. Well, this is something that we would expect. And for some reason, with valence, it's lower, but still a positive correlation. Okay, then the next thing, we trained an inception architecture on the MEL spectrograms. There is a MEL spectrogram of 299 by 299, which is a standard input to the inception, and it contains about 11 seconds of music. So it's not a complete excerpt that was annotated, but I shift when I train inside the excerpt. And the neural network gets a correlation of 0.49 on the test set. So it didn't perfectly learn whatever people were saying. One other thing that I tried is training a recurrent network on the chroma, and that surprisingly didn't work as that well. So that tells us that something in the music is important, except for the actual pitch that is played. Though for the mode, the pitch itself is supposed to be important. Am I supposed to finish? Oh, okay, this is the last slide. So that's another experiment I did to try to understand what the model learned from this majorness. I took Bach's Well-Tempered Clavier. It's 96 pieces in the first and in the second book, in CPITs from every piece. And my model is trying to determine whether something is major, what is supposed to be major, and something is minor. So the random baseline would be 50%, and the model got 70% accurate. And when I look at the exact results, I see that whenever something is performed not in a happy way, so for instance, something is supposed to be major, but it's slow, it's legato, it sounds sort of melancholic, then the model makes a mistake. So it learned a lot about the what's in the performance, but it also learned something about the mode and pitch. Okay.
Okay, thank you very much. We have time for 2 questions. Maybe I would have a question. Did you also look at chord progressions, or did you count the number of chords in an example to see whether it might be like the distribution of major and minor chords, why people would perceive something as major or minor?
Well, in the first place, in order to look at the chords, you need to have chords. In some of the excerpts, you don't even have any harmonic instruments, you only have percussion. In some of the instruments, in some of the music, you will have only melody. So in order to look at the chords, you will need to, do some extraction. It will be super noisy because sometimes there are no chords. Sometimes it will make mistakes. I didn't look at it. But probably if I sort this music somehow to get the music that is plausible to have any chords, yeah, I could try to look at that. But Chroma does a similar thing already and it didn't work, so.
Okay. Okay.
Yeah, there is a question.
Yes, 1 second, please.
I was wondering what you, how the results might change if you take the duration of your excerpts as a variable. Gigant and so on are working on this, have like short 5 seconds, 7 seconds, 10 seconds, and see how then the categorization works and how your architectural deep learning performs better, although depending on the duration of the excerpt. Because I think you had a fixed duration, right?
Yes, it was 15 seconds. I could I give actually to the neural network a shorter excerpt, 11 seconds. If I give it even a shorter one, then there will be a problem with the annotation. The annotation was done on the 15-second one, right? It's 5,000 songs. I'm not going to redo it. So, and if I give it just, for instance, the beginning, then the annotator might have focused on the, I don't know, last 5 seconds more, or middle, or I don't know. Like I guess it's best to give it whatever the annotator heard. It's more fitting the data.
Would you expect if you had longer, for instance, durations?
Yeah, if I had longer, there would probably be more modulations, and it's probably going to be more difficult for a person to say whether it's major or minor.
Okay, thank you very much again, Anna, for this great talk. And hereby I'm closing this session. Thank you very much for coming, and see you in the afternoon. Thank you.